Hello everyone, I welcome you all in this lecture. So in this lecture, we'll study the VN diagram. This is very important topic in aerospace engineering. N means load factor. I already explained about you what do you mean by load factor. It is how much lift you are having then compared to the weight. That means L by W you can define as a load factor. And we discuss the load factor case for different flight cases. Now what we will do, we will plot the load factors versus speed, and here speed I am taking an equivalent air speed, not the true air speed. As I discussed, when you go higher and higher altitude, the air will become thinner and thinner, so at the same power setting the speed will increase. Okay, if you just write a dynamic pressure at that particular altitude and dynamic pressure at sea level, so you can write like this: half rho v mean sea level you can write, or do you just write here v equivalent air speed, and this is rho sea level and dynamic pressure at that altitude, and this is basically v2 speed. So v2 will become v equivalent air speed divided by rho s. So rho by rho s. So rho will decrease with increase in altitude, so true speed will increase. So so each and every altitude the trim speed will change, right? So for if you want to plot the VN diagram between load factor and equivalent speed, then if you consider the true air speed, you have to draw multiple VN diagram, because the moment you change the altitude, speed will change. So in order to solve that problem, instead of taking true air speed, you have to take the equivalent air speed on the x-axis. So you have to draw only one diagram. Okay, that is good for pilot understanding also. Now, so you can see this line is going, this line is, and this line. So I will explain each and every line. So load factor and equivalent speed clear. First you can mark here n equal to 1 line. See, aircraft is flying steady state level flight. You can mark n equal to 1 line. Now, what is lift? Lift equal to NW and n equal to 1 for steady state level flight case. So half rho v square s into CL equal to W for a steady state level flight case. So if you put CL max, there will be speed. That speed is known as a stall speed. Minimum speed required to sustain the level flight. So you can mark the stall speed here. That corresponds to n equal to 1. But you can see here, I am writing NW, right? So half rho v square s into CL. So I can write v equal to 2NW divided by rho s CL and under root. So if I put a stall speed here, Vs, you have to put Ca max here, right? So at a different n, you have a different stall speed. So that exactly we are denoting here. So all this is stall speed only, corresponding to different n. And here you will put the maximum load factor n max. That can be 3, 3.5, 2, depending upon how strong your structure is. Okay, that's the here plays the aircraft structural engineering. So it is clear that when you put n max here, you will get v corner speed, or you can denote as a v star. That is the case where you have a both n max condition and CL max condition. So what is this case? This is the exactly this case, this point. And if you have a maximum load factor, there will be the ultimate load factor also. See, here immediately the structure will not fail, it will start failing, but after this red line, top one, complete structure failure will be there. So that corresponding load factor will be known as a ultimate load factor. So ultimate load factor, that can be 1.5 times n max or 1.2 times, depending upon how strong your structure is. So I think this line is clear, right? Similarly, when you have an inverted flight, you will have a and CL negative but max in magnitude. So if you put that value, you will get stall speed. Sometimes it can be greater than of a positive stall speed case. Okay, all right. So similarly in lower case also you have a this limit. And if you are flying in a particular altitude, let's say at the sea level, you cannot beyond a speed that one particular speed. So you can draw this line. This all is propulsion limit. So this is a aerodynamics limit, stall, positive stall, negative stall. This is a structure limit. This is propulsion limit. And sometimes it happens that you are diving, so you cannot dive beyond that allowable dive speed. So that limit you can put here. So I think the VN diagram part is clear, and how it has been drawn, it is also clear, right? So along this n equal to 1 line, you can fly at a different design speed, right? Sometimes it happens that design speed 1.2 times Vstall, 1.5 times Vstall, or sometimes 2 times Vstall. So you can move along this line and fly the different trim flight speed. Now you notice one point. Sometimes it's like this maximum limit can be 2 times Vstall, 3 times Vstall, 5 times Vstall, depending upon how powerful engine is this. Okay, and sometimes it happens that your dive speed is more than the maximum allowable speed at a steady state level flight case. So depending upon that, you can draw this line. One more important point is this is the VN diagram without any gust loads. See, when gust comes from the, let's say, this direction, so it will change the load factor. It will change the angle of attack. So let's say if you are flying here beautifully, you may cross for a fraction of second, and then maybe when the gust will go on, then you can come back to the flight envelope. So we'll study how the gust will affect this VN diagram. Okay, beautifully flying here. So if the gust comes, you can go out of the limit. So that means flying here stall condition is dangerous, because any gust comes, it will try to push you out of the VN diagram. This is also called the performance limit of the aircraft. So we'll consider one by one. So first we'll take sharp edge gust, which is not the most realistic case, but first you can consider this. This is a vertical gust, and aircraft is this you are entering. And second one is a graded gust. That means when the aircraft is entering, slowly it is getting built up and then constant. See, when let's say atmosphere is stressy, there is a gusty environment there. So basically you are entering into the gusty environment, right? Consider this case. So in that case, I mean to say, it is like immediately you will not feel this magnitude amount of gust. Slowly it has to build up, right? This one is the more realistic case than compared to this one. Okay. So we'll discuss this one, how we have obtained this change in load factor. So we'll try to derive what is the amount of load factor will be changed due to the gust. So first we'll take this gust and we'll multiply some kind of factor in order to convert the sharp edge gust into the gradient one. Okay, so you can write lift after the gust half rho v square h into CL dash. That means you are assuming with gust only angle of attack changes, not the speed, because speed is a slow variable. It takes time to change, and this is an angle, it can change very fast. So if this assumption is fair, without without gust half rho v square s into CL. So how will you find the change in lift? You subtract this one L dash minus L. So that becomes you can see here L dash was half rho v square s CL dash, right? And L will be half rho v square SCL. So that means this is with gust, and this is without, this is without gust. So you subtract this to L dash minus L, take half rho v square S common, and you can spend CL. This is CL naught plus CL alpha, and alpha plus delta alpha. That means delta alpha is change in angle of attack due to gust. Okay, and similarly you can write CL naught CL alpha into alpha for a without gust case. Finally, this delta alpha you can write. Delta alpha you can write. Delta L you can write half rho V square S CL alpha delta alpha. Now, then how will you find the load factor? Change in load factor. Delta L by W. So you can write half rho V square S CL alpha delta alpha by W. So now let's say this is the aircraft velocity, this is the amount of gust, this is the amount of gust. So finally this is delta alpha. So you can write tan delta alpha equal to Vg by V. So if delta alpha is small, so that you can write to basically delta alpha equal to Vg by V. So if you substitute here, so Vg by V, one V will get cancelled, you will get half rho V S CL alpha Vg divided by W. This will become delta N. Okay, and you can write, actually you can put S down and you can write this. So that means the aircraft has a high wing loading, there is a less change in delta N. When you have more Vg, more delta N. So if the wing loading is light, the change in load factor will be more, right? And if the wing loading is less, delta N will be more. Like for example, glider, wing loading is less, right? So the effect of change in delta N will be more. Okay, that is how we derive delta N. And here V is greater than, much greater than Vg. So that exactly we have derived. Okay, finally. We'll take the numerical example, but if you want to consider this one, now it is clear, right, how delta N is derived. So if you multiply the factor F, so that F is called gust elevation factor. So basically F is less than 1 but greater than 0. So F equal to 1 means sharp edge gust, and F less than 1 means graded gust, right? And that F, amount of F which is less than 1 will decide the effect of graded gust. So anyway, when you are flying a steady state level flight, we have to find out the change with respect to N equal to 1 case, right? A steady state level flight case. That is why 1 plus minus delta N is written. And another type of gust is cosine gust. So cosine, we see, you can take a Q as a pitch rate versus time. So you might have experienced the turbulence in a flight. Sometimes it may last in just 1 minute 30 seconds, and sometimes it can last after an hour. So it is continuous in nature, but we approximate in a discrete fashion. So you can write as a cosine one, and this is the maximum amount, and this one is on axis you have a time, and this is Vg as a function of time. So you can write Vg as a function of time equal to maximum amount Vg by 2, 1 minus cos pi t divided by capital T. T is a time required to reach the maximum value of it. So this is in terms of time you have written. So you can actually convert this in a Cartesian. Okay, so you just convert time into distance, because in reality you have a gust in 3D space. Take total length of a gust is 2x, maximum on Vg same. So what you can write, speed equal to distance upon time. So speed equal to x by t you can write, and you, if you cover the 2x distance, you can write 2x divided by total time is 2t. So v equal to x by t, v equal to x by t, x distance time t, and same speed v equal to 2x distance divided by time 2t. So t time and 2t time. So that means t by capital T you can substitute here. So t by capital T is small x by capital X. Final expression will become Vg as a function of x, Vg by 2 1 minus cos pi x by capital X. So x is this distance, this much, 2x is the total distance, and small x is the generalized distance at any point. Now we'll take some numerical example. So consider the weight of a aircraft is 10 kg, density 1.2256 is sea level density, and wing area is 2. That means wing loading is 10 by 2 5, right? So it is a very small UAV aircraft. You can consider this. CL alpha 5 per radian. You will find out delta n equal to 0.062 V into Vg. Stall speed you can find out. Take CL max 1.2. You will get 8.16 meter per second. CL. Now, so take Vg equal to 10 meter per second. So what is delta n? 4.86. And second case, when Vg equal to 1, you will get at 20 meter per second, you will get delta n equal to 1.2. So here at Vg equal to 10 meter per second speed, at stall speed the delta n is coming 1.486. That means if you have a stall speed 4 delta n, you are getting 4.86. If you are flying n equal to 1 at a stall, so if you add 1 plus delta n, it becomes 5.86. So clearly you are out of the envelope. And let's say if you are flying at a 20 meter per second, but gust is 1 meter per second, so delta n will be 1.24. So that means let's say if you are flying at 1 to 1 plus 1.24, that becomes 2.24. You will be inside the envelope if you have a nmax 3, let's say. Now consider the commercial aircraft. Let's say weight is 41000 kg and s equal to 125 meter square, CL alpha 5 radian. So you will get n delta n equal to 0.0009522 V into Vg. So that means the effect of delta n is very less. For example, if you consider the commercial aircraft, so that is why commercial aircraft can sustain a large amount of gust than compared to light aircraft. So one example I have taken light aircraft when the weight was 10 kg only. So how sensitive was with respect to the wind. But here this is 30 is coming, right, and here is only 10 is coming, right. Here is 30 is coming. You can see this. So what is the typical load factor range? 2.5 to 3.8. 3.8, that means you can bang the aircraft 75 degree, already explained. So you can see this L cos phi equal to W, and if you put n equal to 75, you will get n equal to roughly 3.8. And for 2.5, phi equal to 66. Phi is the bank angle. Okay, I have already explained in the manual road lecture. So if you find out the stall velocity, put 2 weight multiply by 9.81 to convert into the Newton. Important part here. People do the mistake here. People generally forget to multiply 9.81. Sea level density 1.2 is what? CL max, and wing area is 125. So we'll get stall speed 66 meter per second. Cruise speed is 150 meter per second. And you can see relate the cruise speed with stall speed 150 divided by 66. That means cruise speed is roughly 2.3 times of a stall speed. So now here you can see delta n, it is coming 1.4. So beautifully, if you are flying at a 1.4 is coming, so 2.4 you are inside the envelope only. So what was the wing loading comparison? If you convert into Newton, 10 into 9.81 by 2, 49 Newton per meter square. And for commercial case, 321768. So wing loading is more here in this case. That is why effect of delta n is less. So 3217 divided by 49. So that commercial aircraft has a 65 times more in terms of wing loading. If you divide this by this, so you will almost 66 times wing loading is more than compared to light one, light UAV. You can see the light UAV case we have taken. The weight is 10 kg, wing area is 2, CL alpha is 5, and rho is 1.225 kg meter cube. Sea level density. You can see how the load factor and max we have marked 2.5, and we have marked this 10, 20, 30, 40. So we have found that the stall speed 8 point, right? 8 meter per second, right? So corresponding to this, we have marked the stall speed, and corner speed also we have marked here, and this is the max limit, and this is a design cruise speed. So this is Vg equal to 1. So what we are getting actually at load factor, see, the stall speed is 8.16, right? And for Vg equal to 1 case, delta n is 1.2, right? So if you are a near stall, so if you are out of the envelope, but if you increase the speed, let's say at a design speed, for example, let's say if you are flying at 20 meter per second, so in this case you will have a change in load factor 1.24, right? And plus yes, if you are flying a 20 meter per second, you have a change in load factor 1.24, right? So 1.24 plus 1, 2.24, that means it will be less than 2.5, so it will be inside the envelope only. So Vg equal to 1 meter per second. This kind of aircraft, the aircraft can sustain the gust. But if you have a more than 1 meter, let's say for example 2 meter per second gust, 3 meter per second, you will be out of the envelope throughout the speed range. And this is a design cruise speed you have marked. So how much you are getting the speed? Near around 28, right? So 28 divided by, so roughly more 3.5 times, let's say you are taking the design speed, then compute the stall speed. Is your choice. You can take the design speed, this also, this also, this also, this. It should be more than stall speed, at least 20% more than stall speed, right? Okay, so I hope these things are clear to you, and how you have drawn the gust also. Why I have taken the two example? The two example I have taken because if your aircraft is very light, 10 kg, 20 kg, and if you are, it is a good chance that you will go out of the envelope if you have a gust. But if you have a commercial aircraft, so the gust will affect less as compared to the, see why I have taken the two example. One is UAV, another one is commercial one. Light aircraft is more, that I mean to say light UAV is more sensitive to gust, and already we have seen with the example how the delta n expression, right, value we are getting, and also for a commercial case. So why, what I'm trying to say, if you are flying a very close to stall, right? So let's say stall, and in this case if gust comes, you can go out of the limit. If you fly at a higher speed, the effect of the gust will be minimal, will be inside the envelope only. So that is how the fighter aircraft can sustain a gust. But small light aircraft which is flying very low, it's very sensitive to gust. Okay, so as a pilot, what you will do, you will increase the speed, right? Okay, but I mean to say, uh, when you increase the speed, but let's say already if you are flying here and you are out of the limit, then increasing the speed doesn't matter at all. It will not bring you back inside the envelope. So you have to be very careful that at what load factor you are flying. At that load factor, when the gust comes, are you having enough margin to increase the speed? That you have to see. You have to see the aerodynamic limit also, structure limit also, as well as the propulsion limit also. all three together. Okay, keeping gust in mind. Now the question is, how will you draw the gust line? So what is the delta n? Delta n we have derived, and also we have seen that delta n is a function of Vg only, Vg power 1 only, and also V power 1. You can see here. We have derived, right? Delta n is proportional to V power 1 and Vg power 1. So if you let's say if you are want to draw the gust line, what you will do? You will start from n equal to 1, and let's say this is your one gust line, and another gust line, and another gust line, and another gust line. So let's say this is Vg1, Vg2, Vg3, Vg4, Vg5. So clearly Vg5 is greater than Vg4, greater than Vg3, greater than Vg2, greater than Vg1. So you can consider this way. This is a 1 meter per second gust, 2 meter, 3 meter, 4 meter, 5 meter, or 1, 5, 10, 20, 25, whatever. So that means if the gust speed is increases, so delta alpha will increase, so delta n will increase. So if the higher gust amount of gust will hit, so you have a chance to go out of the envelope. And why I am plotting the straight line? Because already I have shown to you the delta n is a function of only v to the power 1, and this is fixed Vg. So although you are inside out of the envelope, let's say if you consider this point, you are flying, suddenly gust comes and you are out of the envelope. But if you increase the speed, you will be inside the envelope only. Okay, but here in this case, whatever you increase the speed doesn't matter, you will be out of the envelope only. So that you have to keep in mind. Similarly, you can draw the mirror image, and that will be the case for negative load factor. Okay, this. So I hope the thing is clear. Again, I am telling you, in order to draw the Venn diagram, take a load factor on one axis and decide the maximum load factor. For example, 2, 2.5, 3.8. Like commercial aircraft, already I told that 3.8, and why it can bend to 75 degree. Okay. If you have a more strong structure, more load factor will be there. Okay. And again, as aircraft design engineer, if you design more structure weight strength, aircraft weight will drastically increase. So you have to have a compromise. Now, you take equivalent airspeed. First thing is to find out the stall speed. Okay. And then find out the corner speed, so that these 2 points you can locate. And based on the diving speed criteria or max speed criteria, you can draw this. And based on that maximum load factor, you can draw this line. Take a ultimate load factor 1.2, 1.5 times of n max. Draw this line and mark this as a so that you can actually clearly say that this is my structure failure case. Similarly, for the negative load factor case also, if you have any problem of choosing this limit, you can simply take a multiples of stall speed 2, 3, 4, 5 and draw this line. Okay. And if you want to have any confusion in selecting the design speed, you can select 1.2 times V stall, 1.3 times 1.3 times V stall, 2 times V stall as a design cruise speed. You can see at a different you can see the different trim speed how the gust is affecting. So that you can have more feel. Right. So this way you can actually draw the Venn diagram. And if you have any doubt, please ask me. I will try to explain you. In this lecture also I have taken one small UAV aircraft and one commercial aircraft. Commercial means Boeing Airbus A20 I have taken as example, and one small light UAV comes under the small UAV configuration in small UAV category. So by comparing these two, you can see that the in which case the gust is more sensitive. So it is the small UAV case, not in the commercial case. So with this example, I have tried to giving you the feel for VN diagram, gust, how it is affecting, maths behind it, and I have tried to give you the physical feel for this fundamental of a VN diagram, etc. and gust envelope type of gust. So if you have any doubt, please ask me. I will try to explain. Thank you very much. We'll meet in the next class.